Good morning, everyone, and welcome to Team Straw Hat's Technical Senior Design Project Presentation and Project Demonstration. My name is Evan Peelen, and along with my teammates Victor Madrid and Tate Harsch-Hudspeth, we'll be presenting and demonstrating our project, the Seer. Our faculty advisor is Dr. Mohamed Salem, and our industry advisor is Joe Reid. Our team's technical presentation will follow the displayed format.
Start off with the problem. The direction arrival, or the DOA, is a method of finding out from where an incoming RF signal is from. In finding the DOA, the most common methods do not account for many things like multipath, constructive, destructive interference, very complicated environments, and change. With a non-proportional environment, modeling this inverse problem can be almost impossible. The current existing solutions are a full dimension MIMO that can easily find the direction of incoming signal, but is very expensive and not precise. Triangulation that finds the signal while wasting lots of power, and other alternative methods of the solution are multiple signal classification algorithm, Esprit, Patagram, and SAMV, just to name a few different solutions.
Our proposed solution is to implement a system that uses deep learning to determine the direction of arrival of an incoming low-band 5G signal. This system works well in indoor urban areas since the environment need not be isotropic. Our neural network will develop a model that accounts for the complexity as well as the non-isotropic nature of the environment. Our prototype is meant to be a proof of concept and solves the problem by mapping the EM spectrum through training.
So here are the marketing requirements. The system must streamline the process. It must work under acceptable range. It can be modified for other environments through neural net training. It can handle noise. The system works within low band 5G signals. The system must have an interface, and it must be inexpensive.
The system must be able to estimate the direction of arrival of the transmitted signal with an accuracy of 90% or greater, and it must work for 5G signals transmitted within a radial distance of at least 6 meters. Due to challenges that will be touched on later in the presentation, we reduced our target accuracy from 95% and our range from 12 meters. The system must be able to create a valid model for any environment it is trained in, be accurate in the presence of under -40 decibel watts of noise, work with frequencies in the 600 to 850 megahertz band, have a GUI that displays real and accurate data within 60 seconds, and the prototype must cost less than $600.
Next, we have our comprehensive system diagram. Utilizing a HackRF1 paired with a ported pack, we broadcast a 1 kilohertz constant wave at a carrier frequency of 750 megahertz to an array of 3 receiving antennas. Each antenna is attached to a RTL SDR as the received signals are then processed by a Raspberry Pi, saving and sending the processed signals to an external hard drive. A CPU then accesses the external hard drive, training and testing the neural network. Once complete, the neural network makes a prediction of the direction of arrival of the transmitted signal, displaying the results on a graphical user interface.
Once the measurements have been collected via Latin hypercube sampling, the data goes through FFT signal processing. We then extract the magnitude and convert it to decibel watts. Before extracting the phase, we divide the complex phasors of the antennas from the reference, resulting in a relative phase difference. Then skip to the FFT bin with the signal peak and only keep that bin of interest, taking a moving average over 1,000 bins. These matrices are then saved as binary data files and uploaded to the cloud, where they can be accessed by the other members of the team. They are run through our data extraction Python code, which only keeps the values of interest that will be passed to the neural network. Once these are compiled into a CSV file, they are used on the neural net for training. Once the neural net has been trained, the model architecture and weight arrangement is saved and validation data is collected. These measurements have never been seen by the neural net and test the system's ability to estimate based on unseen data. After running the validation measurements through the trained neural net, the results are displayed on the team's GUI.
Next, we have our team's anticipated risks. Utilizing many peripheral devices, the team would anticipate hardware risks, including an uncontrolled RF testing environment, limited USB port connectivity and power output, and signal degradation, which could potentially lead to non-representative data useless to our neural network.
So along the way, we had a good amount of challenges, such as limited lab equipment, delay in the funding. Our CPU couldn't handle the level of computation because of its age. Our CPU was from 2011. Our CPU could also not drive 5 SDRs due to the lack of available output power. And because of that, we had to switch, because of those two reasons, we had to switch to a newer PC made in 2015. After synchronizing the RTL SDRs, we analyzed a phase drift in our data that invalidated all our phase-related data in our system. And in regards to the software, since most of the libraries we used were open source, there's little to no documentation on anything we used, and most documentation we found were geared to other specific applications in Keras and New Radio. Here's an example of a hardware challenge we had to overcome. The hack RF that we used for transmission, after some analysis we found had a faulty mixer that shifted the frequency over by 40 kHz, which you can see in the graph below, where we're transmitting something at 750 megahertz and is shifted to the left. Another quick example is how we had RTL SDR receiver created unwanted interferences due to long-term exposure to high gain radiation, which you could also see in the graph below. We're only transmitting one wave, but there's multiple seen.
Corresponding to our engineering requirements, the team will be displaying 7 tests. Test 1C satisfies engineering requirements 1 to 4. Test 2A satisfies engineering requirements 1 and 3. Test 2B 1, 3, and 4. Test 4 satisfies engineering requirements 1, 3, and 5. Test 5 satisfies engineering requirements 1 to 5. And lastly, Test 6A and 6B each satisfy engineering requirements 2 and 5. In Test 1C, the team would attempt to verify that our hardware and testing environment were representative of the team's expectations when transmitting and receiving RF waves. Conducted in an outdoor urban environment, this test would be taken at distances of 1 to 10 meters. Both the transmitter HackRF1 with porter pack and receiver RTL SDR would be used to transmit and receive a low-band 5G signal. After receiving the low-band 5G signal, a computer running our team's data extraction flow graph would extract both the magnitude and phase of the incident signal. Through conducting Test 1C, the team was able to successfully find the path loss exponent and corresponding variance between the distance versus received signal power trials. The team will calculate the path loss exponent for their outdoor urban environment to be 2.422 plus or minus 0.19 dB watts per meter, as displayed below the plotted graph. Located in the table to the left, the team has displayed typical path loss exponents found within common environmental settings. In the case of the Seer's test environment, our team's calculated path loss exponent is representative of the environmental settings found in an outdoor urban environment.
The goal of Test 2 is to use various RF propagation models to assess our Keras model's ability to handle relevant data. Our model attempts to solve our multi-output regression problem. Test 2A handles the ideal free space scenario, and Test 2B handles a more complex scenario representative of our final testing environment. To make the JTC simulation more complex, we factored in a white Gaussian noise level corresponding to the amount of noise present in previous hardware tests. The JTC model also accounts for walls and obstructions in the environment. Both of these tests were successful.
Before we go any further, we would like to very quickly explain what a neural net is and how effectively it works in our project. A neural net is much like a very large function consisting of neurons, and each neuron is a weighted sum of all the inputs. So stepping back, we can see that a neural net can effectively model what our environment looks like regardless of what it is. This particular function that the computer creates solves an inverse function problem caused by interference, multipath, and etc.
Using 25 validation samples, our model produced an average difference of 0.38 meters for R and 4.42 degrees for theta, using the freeze equation, and 0.88 meters for R and 11.9 degrees for theta, using the JTC with added noise. The added complexity of the JTC model showed us that our physical system would need more layers or weights to capture the complexity of the environment. Test 2 results verify that our neural network is able to achieve the accuracy stated in our original ER1.
So here we are at Test 4, where the team attempts to make a 5 SDR coherent system by daisy chaining the clocks as depicted below. And here's a graphical representation of how our results look, which are good, since the amplitudes of each clock signal match up and there's only a 0.019 nanosecond delay between the first and the second SDR and a 0.012 nanosecond delay between the master and the final output puppet. But ultimately, we found that applying 5 SDRs to the system was not going to work. Due to the lack of output power, we had to cut down to only 3 SDRs, resulting in this test being a failure.
Since 5 SDRs together require 1.35 amps of current, we added a USB hub capable of supplying 1.2 amps from a wall outlet. This did not solve our power issue, and the RPi-4 was not able to run all 5 SDRs. Our flow graph would run for a few seconds, then the SDR would disconnect and become unrecognizable by the system on chip. We tried running them at the lowest allowable sampling rate of 256 kilosamples per second, as well as running the flow graph using a PC with an i7 core processor to no avail.
Next, we have Test 6A and 6B. The goals of both tests were to confirm that our antenna array power and phase data will be useful to the neural network. The team would expect to review attenuation constants representative of the Seer's test environment, and it is to be noted that Test 6A was a success. Test 6B would be conducted in a very similar manner to Test 6A. However, in this test, the antenna array phase would be calibrated. The team would view the received signals via FFT plots, looking for potential phase drift, which would result in useless neural network data. This test was a failure. To conduct both Test 6A and 6B, the transmitter and receiving antenna array would be elevated off the ground plane and set to equal heights. 3 trials would be conducted from 1 to 6 meters in the Seer's test environment. A Raspberry Pi would run our team's data extraction flow graph, saving and uploading the magnitude and phase from each antenna to an external hard drive.
So for test A, we found out that the extracted magnitude did correspond to a distance measurement between the receiver and the transmitter. For 6B, we found a phase drift within the analysis of our data that ultimately made this data useless because the target was distorted by this effect. The team theorizes that the SDRs developed a heating issue over synchronizing the clocks and the removal of heat sinks in the process.
The table displayed here displays the Seer's prototype costs and major system components, as well as the quantity and price of each. With all these system components considered, the Seer would have a prototype cost of $405.23, satisfying engineering requirement 7.
And here's the schedule that we had throughout the year, starting in August last year and then ending up to barely last week.
To meet our original engineering requirements, the team would need to design an external power supply that also functions as a USB hub capable of powering 5 SDRs with 275 milliamps of current each, allowing bidirectional data flow to and from a USB port. A synchronization of SDR clocks via highly accurate temperature-steady external clock would need to be included. If the team could ensure that the SDRs formed a coherent receiver without any phase drift, the team could accomplish greater than 95% system accuracy up to 12 meters, satisfying ER 1 and 2. Team Straw Hats have created a GitHub repository with all of our project codes for both the final 3 antenna array and 5 antenna array in hopes that a future group of engineering students will continue the work we have started. Thank you for joining us. We will now entertain questions from the technical body.